actually much better timing than the chair of the session. So the next speaker is José Caballero. Did I pronounce it right? It's easy for me. From the Centro de Astrobiología in Madrid. José.
Здравей, добро утро. Благодаря на организаторите. Казвам се José Caballero, and I'm an astronomer of the Spanish Centro de Astrobiología, Center of Astrobiology. I'm going to talk on exoplanets around cool stars. Cool, not Jaco, not Gotina Zvezda, Studena Zvezda, okay? But I slightly modified the title, Exoplanets around cool stars with carboness and a surprise. Astrobiologist, biologist, chemist, please stay tuned at the end because you will like it. Now, start with the beginning. At the end of the session, Didier Queloz, no longer will talk about his discoveries of 51 PEC-B 27 years ago and how had changed all this thing of detecting exoplanets. At the beginning they were giant. Now our aim is to detect exo-Earths, which, as has been said before, it is easy to do around the smallest stars. What are the cool stars? Most of you have seen this, and if not, if you understand this diagram, then you will learn half of the astrophysics, because half of the astrophysics is here. This is the Hertzsprung-Russell diagram. At the bottom is the color of the spectral type of the effective temperature. Cool are there, hot this way, and in vertical is the brightness. The brightest stars are at the top, the faintest stars are at the top. Our stars... No problem. These Zvezda are here. Our stars are at the bottom right, the coolest, the faintest. Yes, there are M stars, these later spectral types, the coolest ones, with planets. For example, the closest one to our Sun, Proxima Centauri, is an M12 and has not one planet, by the way, discovered by a team led by Guillem and Gradas from Spain, but has 3 planets. The third planet also discovered by a team led by Alejandro Suárez Mascareño, another Spanish guy. Before, we saw the spectra of TRAPPIST-1c. TRAPPIST-1c is one of the 7 planets around the star TRAPPIST-1. TRAPPIST-1 is the smallest planet, the smallest star, the coolest star with known planets. It has a mass of 0.1 solar masses, 10% of the solar mass of the mass of the Sun. This diagram was done by one of my PhD students. In the bottom is the semi-major axis, the separation between the star and the planet, and the vertical is the luminosity. The top right, you can see some color circles: Mercury, Venus, Earth, Mars, Jupiter, Saturn, without the rings, Uranus, Neptune. The objects between luminosities 0.1 and 1,000th of the luminosity of the Sun are M dwarfs with planets. The red are too hot. The cyan are too cold. The ones in blue in the middle are supposed to be in the habitable zone. Maybe this sketch is simpler. You have again the orbital separation at the bottom, and instead of the luminosity, we have the mass of the star, because the stars that are in the main sequence in the Hertzsprung-Russell diagram, they follow an easy relationship. The red lines indicate the capabilities of our instruments. This one tells us that we can detect planets that are below that line. So that means that if we want to detect with current technology planets in the habitable zone, we have to look at around stars that have masses of 0.2, 0.3, 0.4 solar masses, which correspond to spectral types between M5 and M2. Problem of M-dwarfs. These M-dwarfs are cool. This is what it was in the title. That means that in the optical, in the visible, they emit not much energy. HARPS, the spectrograph that Maria mentioned at the beginning, operates in the optical, where the flux of the M-dwarfs is rather scarce. However, if you want to observe in the near-infrared, you will have plenty more photons for doing spectroscopy. Actually, in the near-infrared, you have something else. If you observe only in the optical, you can see the Rayleigh scattering of the haze of the atmospheres or some atomic species, especially of alkali lines, sodium and potassium. But if you want to detect molecules, you need to go to the near-infrared or even to the mid-infrared. Here I'm showing water vapor. There is another thing, which is the activity of M-dwarfs, which is more visible in the visible. The field dots are data, radio velocity data of a star of the same spectral type as TRAPPIST-1, and you may think that there is a planet there. But that's just activity, because if you observe it in the near-infrared, the radio velocity curve is completely flat. So there was a competition at the beginning of 2000s for building the first spectrograph that, in the high resolution, a planet hunter that operated in the near-infrared. Then there was the British, the Japanese, the Italian, the Americans, the French, the German and the Spanish, and as you can imagine, the first spectrograph to operate was Carmenes. Carmenes is like HARPS and NIRPS, but together and without a gap in the middle, and operating since 2016. Carmenes, of course, is the name, it's an acronym. The C and the A are Calar Alto, that's an observatory that is in the south of Spain, in Andalusia. It is not in the Canary Islands, it's in the south of the mainland, in Almeria. The R is high resolution. It's about between 80,000 and 100,000. This is, as you can imagine, of resolution. The M is M-dwarfs, because it's especially devoted to look for planets around M-dwarfs, which are cool, faint, small, so-so. And we look for exo-Earths. They can be gaseous planets like Bespin, desert planets like Tatooine, water planets like Camino, icy planets like Hoth, jungle planets like Kashyyyk, or even inhabited planets like Coruscant. Near-infrared. Actually, Carmenes was the first working in the near-infrared, and the first and only for the moment working simultaneously in the near-infrared and the visual. So in one shot, in high resolution, we cover from 0.5 microns to 1.7 microns. That is a lot in high resolution. For the moment, it has not been equaled. The E is for HL, which is the type of spectrograph that we are using, and actually we have two spectrographs in vacuum, keep at accuracy of 1 millikelvin. Carmenes is the name of the instrument, and Carmenes is also the name of the consortium that built the instrument. 11 institutions, 5 in Germany, 5 in Spain, and the observatory that at that time was half German, half Spanish, with more than 200 people working on that, about 100 Spanish, 100 German, and the budget was about 5 million euros, 2.5 German, 2.5 Spanish, so we can see that Carmenes is half German, half Spanish. For that reason, I designed this logo, which is the Spanish part middle, and the German part, Bauhaus. For those who like design, you will recognize it, and this is the Solmido Bauhaus. Cármenes is also a scientific project. It's a scientific project. When you build an instrument for an observatory, you are rewarded with observing time, guaranteed time observations. We were given 700 clear nights for observing M-dwarfs. We observed something like 300 M-dwarfs, and last month we had already 4,000 citations of our 200 and so entries. It's about 150 referee journals in just 6 years. 10 examples. We started with the preparation of the sample. That was our first paper. That was by my first PhD student, and it was just observing and preparation for not wasting the Cármenes time with other telescopes, identifying the stars. When we observed the first stars was, of course, known systems, and that was led by Trifon Trifonov, now in the middle of the room. And actually, just by chance, we discovered a couple of new planets where they were not expected. At the beginning, we discovered the easiest ones, the ones that were not Earth mass, but Neptune mass, I mean, a bit heavier. But that was a surprise, because up to 2015, the competition between teams on exoplanets, between the Swiss, the American, the Japanese, the Canadian, was always confronting. And when we arrived, we said, okay, we come here, we come with this data, let's work together. We could publish this planet alone, which is the bottom right in red. We had the signal, but we prefer to put everything together with HARPS, which is of the same quality more or less, and with HIRES, Keck 10-meter telescope, which is worse than Cármenes. But we put all of this together, and we published everybody together. We also may publish one spectrum per star, because it can be done, it can be useful not only for astrophysics, for exoplanets, but also for astrophysics in general. And actually, apart from the careful determination of mass and ratio of the star, mass and radius of the star by Vasilin Kostov and his eclipsing binaries, when they are not eclipsing, you have to derive the mass and the radius of the star carefully, because the mass and radius of the planet depend on the mass and radius of the star. And you have to do it very, very carefully. We also discovered something that were not expected. Around GJ 3512, we discovered a planet. This 3512 star is of the mass of TRAPPIST-1, 0.1 solar masses. We discovered a Jupiter mass planet. That was unexpected, and that's a challenge for theoretical models. All of them are unable to simulate the formation of such a massive planet around such a small star, such a cool star. Also, with Cármenes, we found that we could do something that cannot be done before, apart from radio velocity surveys, and was investigating the atmospheres of the planets, and in particular, a line in the near-infrared that has not been covered before in high resolution. That was helium-1. That was quite a surprise, published in Science, 150 citations already, and it was published just 3 or 4 years ago. Why is it important? Because for the first time, we can investigate the structure of the atmosphere and the wind, but especially the structure, what is the temperature and pressure profile of the atmospheres. Up to the discovery of this helium line, it could not be done. Of course, with Cármenes, we have found the planets for which we have designed the instrument. By the way, I was the project manager of Cármenes as well, so I'm very, very proud of Cármenes, and especially of this planet, because the Arizona Observatory has a list of planets sorted by Earth Similarity Index. I mean, the planets that look like the most to the Earth. And T-Garden B is the exoplanet with the largest Earth similarity index because of the size, insulation, radius, and so on. Number 2, with Carmenes and radio velocity and with HARPS, you can only measure the minimum mass of the planet. With transit photometry only, you can measure the radius of the planet. But if you have both radio velocity spectroscopy, mass, and transit photometry, radius, you can get the density of the planet, the bulk density. And then you can do models of the interior of the planet. In our initial sample, we have found now 4 planets that transit their stars, plus the ones that we are following up detected by the NASA space mission tests, that they are something like 20 or so. So we have a lot of follow-up objects, planets, for which we can derive the mass and the radius simultaneously. And number 1, Trifon, you win, again. A nearby transiting rocky exoplanet that is suitable for atmospheric investigation. Trifon Trifonov, there, Bulgarian, second author myself. What did we do? Okay, so we were observing with Carmenes about 300 stars. M dwarfs, they are not the bright ones like Vendimiatrix that may observe with HARPS 3 and the spectrograph that has large, but an M dwarf like this one, GJ486, which is number 486 in the Gliese catalog. We measure radio velocity with Carmenes and we see some signal, and the signal was quite apparent, and then we started to look for transits because we could think that they could be. The day after the test data were public, we saw, oh, there is a transit. Well, actually there are 19 transits in the data, so we could determine the mass and the radius of the star, the equilibrium temperature, and starting modeling the main parameters of the planet. Maybe they could be rocky, it could have an atmosphere, it could have a large tectonic activity. That was published just 1 month before the cycle 1 of James Webb, and it was one of the planets that will be observed with James Webb. And then more recently, we had a second paper with better data, because we use ESA chaos data and new Marunex for the radio velocity, and then we could put GJ486 is the black star at about 3 Earth masses, 1.3 solar radius, super precise. There you can see Jupiter, Saturn, Uranus, Neptune, the Earth, Venus, and all the rest, the colors and symbols, are transiting planets for which we have already mass and radius, and we can model the interiors. And actually, we measure the interferometric radius of the star, so that means that we know quite well the radius of the planet, of the mass and radius of the planet, and we could model the interior of the planet. And for the first time, making some things of, okay, can have mantle, upper and lower, and a core, outer and inner, and can generate magnetic fields and so on. That is something that we will go on investigating in the future. So of the 7 systems inside 10 parsecs that have a transiting planet, 3 of them have been discovered by Carmenes. Actually, Carmenes have discovered half of the planets around stars below 0.2 solar masses. I mean, half of the cool planets have been discovered by Carmenes, and this is the surprise. And it is Back to the Future in 2000 I started my PhD, and one of the chapters was studying the habitability around ultra-cool dwarfs, even cooler than those ones. And I said in my thesis years ago that since there is no photons in the optical, but there are photons in the near infrared, there could be photosynthesis, and I put example of bacteriochlorophyll B. Years later, I restarted this project, which is ExoPhot, photosynthetic systems in exoplanetary systems. For the freakies, this is Namek in Dragon. So in the first paper, we investigated 5 photopigments, chlorophyll A and B, bacteriochlorophyll A and B, and a synthetic one that we call PHOT0 that I will explain later. 3 stellar types: the extreme, the hottest one that can have planets, A5, the coolest one, about M8, and in the middle, solar type, G2. 4 different atmospheric types, different oxidation, reduction, similarity to the Hadean, to the early Earth, and putting everything in the cauldron and cross-matching, overlapping, and then you get a final absorbance, and you can see a peak at about 6,500 angstroms, and another one at 4,000 angstroms. That is the peak for the sun. But depending on the, as suspected, on the photopigment and the spectral type of the star and the type of atmosphere, one photopigment has a thickness larger than the other. We are now working on the same, but instead of 100 photopigments, instead of 3 stars, a lot of them. And then I go to the end. PHOT0. PHOT0 was the synthetic photopigment that I mentioned before. We presented it in PCCP, and it was a surprise for me. It was the cover page of the journal. A plausible, primable pigment on Earth and rocky exoplanets. So maybe I am presenting you the first, the precursor, the LUCA, L-U-C-A, of all photopigments on Earth and possibly on other rocky planets. And that's all. Thank you very much. Благодарю.
Thank you for the perfect time. Questions?
Identify yourself, because Olga, and there are some people listening via Zoom.
Yeah, Vince from the University of Minnesota. A very general question. What do you mean by habitable? And is there an agreement of what habitable means? Is it based on water? Is it based on what we know of biological systems on Earth? Is it based on extremophiles? What does that mean by habitable?
Yeah. At the Center of Astrobiology in Spain, we work also on extremophiles and so on. But in astronomy, we are very simplistic. I follow exactly the same definition of Vasilij Kostov has used, which is the presence of liquid water on the surface of a rocky planet. Just liquid water. That means from 0 Celsius to about 65 Celsius. This limit in 65 is not because of the naturalization of the proteins, because you know that there are extremophiles that can survive hotter, but because of atmospheric issues, the runaway effect. So when an astronomer says this planet is habitable, is because the equilibrium temperature is between 0 and 60 Celsius. Of course, it depends on the albedo of the planet, which you don't know, if the planet has an atmosphere that we don't know, and so on.
And is there, just by curiosity in the field, an agreement about that, or are there some outside?
It's kind of
maybe definition of habitable.
It's kind of ad hoc for us. Of course, there are some researchers who know. Well, I must say. I'm the scientific supervisor of a movie for planetariums that will be Dark Biosphere, and we will talk on the life under the surfaces of the planets. Like in Mars, we can have permafrost. In Europa, we can have living organisms below this. This is what the astronomers in general, we do not use, but we are aware of it. And actually, one might wonder that most of the life in the universe can be below the surfaces of the planets, because even on Earth there are some estimations that 80% of the biomass, the total biomass, is not on the surface but below it.
Very good. Thank you for the clarification.
Hi, this is Savis from YouTube. Amazing talk, very, very interesting. So I'm just wondering if you can put in perspective where these M dwarfs, in terms of their stellar evolution and the conditions that these planets have gone through, would that be more suitable for life or less suitable for life?
Okay. In terms of evolution, M dwarfs have the longest life of all the stars in the main sequence. That means about 3, 4, 5 times the life of the universe. So they have this advantage that around M dwarfs, life can develop for eons. We are looking for them now because they are easier. For the moment, looking for exo-Earths around G25 stars, solar-like stars. As has been said before, it is complicated. So, are M dwarfs the best? M dwarfs, they have some disadvantages. Somebody mentioned before activity, magnetic activity, flares, flaring activity, but not all of them have it. The most important thing is that 70% of the stars in the galaxy are M dwarfs. So it is not a matter of better or worse than a G dwarf. It is that just by chance most of the life, if exists in our galaxy, would be around M dwarfs.
So just to follow up on that, so if it's that old, would you predict that it would have a mantle that would be, still hot, the planets, because everything would just be cold at that point,
The planets get cold as well.
Yes.
And there are the ones that we are discovering right now with the transit and radio velocity. Since they transit, the detection method is biased towards the closest planets. So the planets that we are discovering right now and that transit are very close. That means that they have equilibrium temperatures of a few hundreds of kelvins. The one that I showed you before is 700 kelvins. It's not habitable. 700 is not too much in comparison with the temperature in the center, of course, of the planet. But that will depend more on the mass of the planet. A Mars mass planet will cool faster than a super Earth, a free Earth mass planet. So in the end, it does not depend on the star, but on the planet itself.
Ok, le agradezco mucho por la presentación. Disculpe.
Gracias.
My name is Peter from the Sofia University, and I may overheard that, but did you mention 100 photosynthetic pigments? 100?
Yes.
So
yes.
Can you elaborate on that? Is that synthetic pigments or proposed?
No. Actually, they are pigments in general. There are some tetrapyroles and so on. So we made a extensive bibliographic search, and one main thing of the chlorophyll and bacterial chlorophyll, but so we have combined all of them. For the moment, synthetic ones, we started with just with 4.0. It was published this summer, but as soon as we have manpower, we will start adding radicals and more rings and so on, and I'm trying to synthesize chemically, for example, chlorophyll A from 4.0. But in the literature, there are a lot of photopigments. It was a surprise also for me.
Hi again, Trifon from MKA and Sofia University. I just want to spark a little discussion about planets around 10 dwarfs, and in particular about the tea garden star, the tea garden planets. Now, you mentioned that they are pretty much Earth-like by many parameters, but one we should really highlight to non-experts here is that those planets are actually tidally locked, which means that one of the side always faces the surface of the sun, right? So the stellar disk. This is the same as Earth and Moon system. Moon always faces one side, so therefore one of the sides is always kind of hot and the other is very cold. Of course, there's a lot of experiments done in the literature and scores that there must be some heat transfer and etc. But this is quite an implication, and I think I'm always been puzzled how they've been classified as Earth-like planets if they are tidally locked. So if you can comment on that, would be great.
I was looking for the slide that is the tidally locked line on top. Absolutely true. I don't know if I should comment the hypothetical potential presence of moons, habitable moons, around these tidally locked planets. The moons would not be tidally locked. Maybe you have seen Avatar, and the second Avatar will come in before Christmas. So Pandora is a moon of a Jovian planet around Alpha Centauri A. The planet is tidally locked, but the moon is not. But something that Trifon and I have found is that, in particular for this kind of planets, these moons are not stable, which comes back to his N-body simulations. Of course, one can think that a living organism can live in the part which is in the transition between the dark and illuminated area, or only in the illuminated area, but it is something that I leave it to you.
Okay. Thank you, Jose, for a great talk. An applause, please. The next speaker is Olga Tchaikovsky. Unfortunately, due to circumstances completely out of her control, she cannot be here, but she will be making the presentation via Zoom. So after her